Okay, now to do the second equation, this is going to be the quadratic, so the pattern is not going to be as simple as just add the same thing each time. There is a pattern. The pattern is the second difference is the same, but you're better off just to keep plugging in the number. So negative 2 squared is 4, and 4 minus 3 is 1. Negative 1 squared is 1, minus 3 is negative 2. And the next one is negative 3. The nice thing about quadratics is I do get some symmetry. So 1 and negative 1 should yield the same result. So should 2 and negative 2. Those should yield the same y value. Okay, and this is just kind of reviewing those good algebra skills that you hopefully remember everything from algebra 1 and 2. Alright, so go ahead and make a guess as to what you think if I just graph these two variables, what my result will look like. And then we'll see if you're right or wrong. Now keep in mind that in our parametric equations, both x and y were dependent upon t. T was the independent variable. X and y are both dependent variables. But when we then graph this on a Cartesian or coordinate or xy plane, it's going to be just like how it was before. It's going to appear that the x is the independent and y is actually dependent upon x, but we always have to think back to the situation. But in terms of graphing, you were going to plot these points. Now, I kind of showed it on the last one with that resultant vector, but on this one, you need to keep in mind that you are going in an order. So the order that I'm plotting these points in matters, okay? And so 1, negative 3, 3, negative 2, 5, 1, and 7, 6. I plotted these points in this particular order as the t values were increasing. Okay, this is the order that my parabola, and the result here is a parabola. Now, I'm putting these arrows where I'm putting them. It doesn't matter so much that you put them exactly in between the points. I'm just saying I put them along the way so that you could see that this is the path of this particle. In this case, it's not necessarily a it's not a raindrop anymore. It could be any type of particle, all right? Or this is kind of theoretical here. But this is the path. This is the third variable. This is the t. So you may be thinking, well, this is overkill just to have a third variable. But again, we're just talking about parametric equations for the first time. So we've got to get the basis down. We've got to understand the language and the notation. And then, later on in calculus, you get to kind of work up to what the application is. Okay? Now, the result here was quadratic. So you can kind of make for yourself, your own guesses as to if one is linear and one is anything else, would that result follow the higher order polynomial? And so that's not anything you really have to know right now, but it's kind of good to notice that as you go through your assignment in class tomorrow. So on the linear one, it was easy to then look at this graph, okay, and then write an equation. For quadratic, this is not so easy. For someone who was in Algebra 2 and right in the middle of a quadratics unit, they should be able to write the equation of this quadratic. Anybody who hasn't really talked about parabolas very much lately, like all of you watching this video, you're probably going to struggle with writing the equation of this quadratic. I'm not going to review how to do that right now. That's not that important for this particular lesson. But tell me, if you had a set of data and you knew it was quadratic, how could you write the equation if you had to? You could always use quadratic regression, okay? And you only want to use that if you know the data is quadratic, but I can see that it is here, mostly because of the symmetry, but also because the vertical component here, or the y component here, was definitely quadratic. Okay, so you could have used quadratic regression here to write this equation. Or there is a way to do it without, but again, not the point of the lesson, so I'm going to move on. Okay, so now we're going to kind of go the other way. In this case, I'm giving you a line with just x and y, and it's linear, obviously. It says line, it's linear. And I'm asking you to write the parametric equations. Now, once again, I'm going to write this down. Remember that t is your true independent variable. Okay, and both x and y are dependent upon t. That's extremely important to remember. So when you write your equations, we could actually be writing our equations as x of t and y of t. You don't have to. It's kind of like f of x or just f. I'm going to keep it simple today. Tomorrow when we actually apply this, you'll see that it will actually be x of t and y of t. So if you have to write two equations down, make the top one as simple as you could possibly make it. And the simplest equation is kind of like the parent function, y equals x, but this is going to be like x equals t. So the horizontal component here is the time component, if you want to bring it back to our raindrop problem. Now, if x is equal to t, and y is equal to 1/2 x plus t, how could you write an equation in terms of y and t? Just replace the x with the t. That's why I made it so simple. Now, there are other equations we could have written. This is definitely the simplest one. And if you were to have made a table and graphed these parametric equations, the resulting line, the resultant vector, would definitely be y equals 1/2 x plus 7. So going this way is a lot easier, actually. Okay, now looking at the next example, I'm giving you the parametric again. Notice that they're both linear. I'm asking you to write a line. So it's kind of like what we did on the first example. This is why I said I was almost getting ahead of myself first example. Now, in the first example, let me remind you of how we did it. Okay. I made a table, I made a graph, and then I used my good Algebra 1 skills to come up with an equation of a line just using x and y. And that will work every time. Okay, but you really don't have to do that on every single one of these problems. All right, let's think about the easier way to do this rather than a table and a graph, because it doesn't say we had to do those, so let's not do that. Okay, first what we're going to do is we're going to solve for t. Now, I could actually do this in either equation, but I'm going to do it in my first equation. So if I have x equals -2 plus t, what does t equal? Okay, t equals x plus 2. Okay, and so that's first. All right, I'm going to put little bullets here. Okay, then we're going to substitute. And guess which equation we're going to use now. All right, so then I'm going to have y equals 4 minus 3, and instead of t, I'm going to write what t equals, which we just found, x plus 2. Now notice I already have an equation with just an x and a y, and all I need to do is clean it up. So then that's going to be y equals 4 minus 3x minus 6, and then writing this in good slope-intercept form, y equals -3x minus 2. Okay? Now, let's go ahead and go backwards just for the fun of it. We're almost done. If I gave this to you and asked you to find the parametric, do you think you would have come up with these two? No, probably not. Probably what you would do is say, hey, I'm going to take the easy way out. I'm going to let x equals t, and I'm going to let y equals -3x, -3t minus 2. Okay, now if you look at these two parametric equations, they may seem completely different, and they are basically off by just an subtracting of 2, okay, or this addition of -2. All right, but they would actually yield the same result, which is this graph right here. Okay, that's it. Bring your questions to class.